So with that, let's get right into the first panel. We're going to talk about focusing on habitable worlds. This ought to be an amazing conversation. This session is kindly sponsored by Northrop Grumman and L3 Harris. So thank you to both of them. So moderating the session is Sean Domagal-Goldman. Sean is the Deputy Director of the Sciences and Exploration Directorate at NASA's Goddard Space Flight Center, where he helps oversee the workforce enabling science investigation across disciplines and science divisions. Sean, take it away.
Thank you, Jim. Thank you, Sean. I am so glad and privileged to be here today for many reasons. I've sat on that organizing committee for many years, and so it's wonderful to be on the other side of it here. Just I want to echo the thanks for all the people that went into planning the things that we've seen all week and the discussions and conversations we've had both here and out there. Again, I'm Sean Domagal-Goldman. I am the Deputy Director of Sciences and Exploration at NASA Goddard Space Flight Center, although I'm also lucky to be here because Dr. Aki Roberge was supposed to be the moderator for this discussion. She couldn't make it because of a family obligation she couldn't avoid that kept her from being here this early in the morning. And I point that out because she's the one that did the work into the slides that we're going to show today, pulling this together and organizing the conversation we're going to have with the esteemed panelists to my right, to your left. A couple notes about what we're talking about, focusing on habitable worlds specifically in the context of the Habitable Worlds Observatory, which is a concept mission that has quite a bit of momentum right now. Slide? Is this off? Oh, that's right. Thank you. Should know this by now. So what is the Habitable Worlds Observatory? It is NASA's next flagship mission after Roman. It's a concept that was recommended to be our top priority and the first thing we do in this decade by the Astro 2020 Decadal Survey from the National Academy of Sciences. What it's going to do or what it's going to be composed of is, I thought Dr. Nicola Fox described this very well the other day. It is going to be a telescope in space with the wavelength range of Hubble, a mirror the size of JWST, and a coronagraph that we've developed by the Roman Space Telescope. And I would add that we've had so many other lessons we're going to incorporate from those missions, including serviceability, and including the programmatic lessons from the Roman Observatory, because that really shows that we can do these complex projects on time and on budget. It's going to do transformative astrophysics. That combination of capabilities is going to allow for a wide range of observations in and beyond the solar system. Closest to my heart as an astrobiologist is the search for life, and the specific goal of searching for signs of life on planets around other stars. Now, this is all enabled, and this is kind of, I think, a special moment. The reason we've got so much momentum is we've been studying concepts like this for decades. And as that's been happening, we'll hear later this morning from Dr. David Grinspoon about the advances we've had in the field of astrobiology, which is the science behind the search for life. And we now have a clear technology plan to enable the very, very difficult and ambitious observations that this telescope is going to try to embark on. And so the next step, as we'll hear about in a bit, is to embark on that path. I could shout, but then the people won't hear me online. I can project my voice, but I can't project it over the internet. So this is the question. Lost it again. Maybe a little battery. We'll give us a microphone. So just grab that. All right, go with the flow here. So this is the quote that you're seeing now. This is from the Decadal report talking about how special the question is that we're trying to answer with the Habitable Worlds Observatory, and honestly some other missions we'll hear about again later this morning. If planets like Earth are rare, our own world becomes even more precious. If we do discover the signature of life in another planetary system, it will change our place in the universe in a way not seen since the days of Copernicus. And for me, as a scientist working in this field, that is such an ambitious thing for us to try to do. And the thing that is special to me as a scientist at Goddard, and honestly a scientist in this field working with the variety of partners we have in this room, is by working together, we can achieve things like this. And that's bigger than just the Habitable Worlds Observatory. This is the specific ambition we have. But I think what's special about what we do together is how we can come together to answer questions like this. Okay, so with that, We're going to go to our panelists. First is Dr. Mark Clampin, who is the director of the Astrophysics Division inside NASA's Science Mission Directorate, which is the organization that's going to be responsible for leading this as part of the astrophysics portfolio at NASA.
Okay, hopefully everybody can hear me. I want to just say welcome to everybody. It's a great pleasure to be here this morning, talking about Habitable Worlds Observatory. So I wanted just to sort of build on what Sean said at the beginning. And one of the reasons we are at this moment, and we're talking about habitable worlds, because I believe this is really, we've entered the golden age of exoplanet science. And some of us can remember when it was still questions like, can you even see an exoplanet with a Hubble Space Telescope, for instance? And when I started at Space Telescope Science Institute at the beginning of my career, the answer was, no, you can't. So we've come a very long way in both the technology that we can use, but also the science that we're now able to do. And Webb at this point is routinely delivering very high quality spectra of exoplanet atmospheres, allowing us to really start studying the chemistry of exoplanets around nearby stars. So the image here, or this video, just really sort of captures what the Habitable Worlds is all about. It's about trying to find small habitable planets and then characterize them to see if we can find evidence of life. The Decadal Survey, I think, correctly identified that this really is the golden age of exoplanet science, and that we've reached a point with the technology and our ability to build large space telescopes and do very high contrast imaging that allows us to really seriously talk about challenges like this. And look, it's still a big technology challenge, but every single mission that the Astrophysics Division undertakes is a one-off, and they're all technically challenging, and we address that by infusing new innovative technologies that we develop to advance the science. So I wanted to just spend a few minutes really talking about, from my perspective, what is our big picture strategy for doing this. And I said a year ago when I first talked about Habitable Worlds Observatory at the AAS meeting that we really want to change the paradigm. And I know every new flagship, we talk about changing it and doing things differently, but we're not really doing things differently, but more we're building on what we've learned from the last 3 or 4 flagships that we've built, and also from the broader range of expertise that NASA has accumulated building very large flagship missions across all 4 science divisions. So we're really just building on lessons learned to try to make sure that we optimize the way we do things. And one of those is that the way you do these big flagships is try to build them to a schedule. And that's really important. And the way you do that is when you start designing the telescope, you already have all your technologies matured and you're ready to go. And the Decadal Survey recognized this, and that was one of their primary recommendations. So we have decided, as we think about how to move forward on Habitable Worlds Observatory, to evolve the technologies and architectures that we've already spent a lot of time and invested a lot of taxpayer dollars in developing. And as an example, we have a large segmented telescope flying at L2 called Webb. It's now TRL9 technology. We know how to build segmented mirror telescopes, and our partners in industry are really tooled up to do these kind of large segmented telescope missions now, having worked on Webb. We're also about to launch the Roman Space Telescope, which is the 2010 Decadal Programmer record. It's NASA's first survey flagship. It also includes a technology demonstration mission, which is a coronagraph. And I got a call last night from my colleagues at JPL, because the Roman coronagraph is currently in thermal vacuum. And they told me that they're really making great progress in doing the final testing of that coronagraph. We expect it to deliver something in the order of 10 to the 8 or 10 to the 9 contrast. To do the Habitable Worlds Observatory, we need to be able to get to 10 to the minus 10, 10 to the minus 11. So we're well on the way with the Roman Space Telescope. We will understand from operating Roman how coronagraphs work in space when you're actively controlling them. and we will, develop the additional technologies we need to support this next mission, increasing the size of the field of view, increasing the size of deformable mirrors, going to active control of the telescope as well as the chronograph. The other things that we want to do are build on the next generation of rockets. Larger telescopes really work really well when you have large fairings, and we want to take advantage of the numerous commercial opportunities now for launching with much larger fairings. And they also give you additional benefits, mass margin, which means you don't end up having to redesign as you go if you run out of mass allocation. And they also provide the volume trades that we'll need for the kind of architecture we're talking about here. We also want to make sure that we have a planned servicing capability. We really want to service this telescope at L2 and be able to go up later on after the first round of the mission and build on the planet finding and planet characterization capabilities that we built into it during the first generation so that we can continue the science that we do with this mission. And there are a number of opportunities. So we see a large opportunity in the commercial world right now for things like cislunar logistics, space tugs, and we want to take advantage of those. So we will design, assuming that we will have those available. And then finally, this is a very hard problem. Building chronographs is very unforgiving. You can lose a significant fraction of your sample size with just a very small change in requirement. So we want to start by building this design with extremely large, robust margins so that we don't have to go back as we design this mission and rework it because we've lost half our sample due to a very fractional change in the requirement. So we understand some of the challenges already. A lot of those have come from what we've learned on Roman, and that's how we'll move forward. So some of you are probably wondering about the conference language in the recent budget that was passed. We will be setting up a project office at Goddard in recognition of the direction in the budget. And that project office will initially be focused on maturing the technologies for this program and stay in alignment with the recommendations that the decadal survey gave us for how we should stage this program. At the same time, we have a number of groups right now that come under this umbrella of START, as we call them. And these working groups are looking at science trades, not just for the exoplanet science, but also for the general astrophysics, because this is an observatory. It will do science that supports the whole of our community, as well as the exoplanet science. And just to give you an example of how inclusive and the amount of interest that this is generating, we have over 1,000 people now involved in working in these working groups. So we're really trying to make sure that at the beginning of this program, the community is engaged, they're buying into what we're doing, and they get to have a voice in some of the science trades and how this telescope will work. So I'm going to just finish up by saying that, people keep telling me, well, this is going to be really hard. And I always try to remind them, yes, it is. That's one of the reasons we do these things, because if you don't take on the big challenges, you can't make the big scientific jumps. And that is what we're going to be doing with the Habitable Worlds Observatory. It's what we expect to do with the Roman Space Telescope, and it's what we're doing right now with the Webb Telescope. So I will finish there and hand over to Courtney.
So our next speaker is, just advance one slide for me, if you don't mind, Courtney. Our next speaker is Dr. Courtney Dressing. She is an associate professor in the astronomy department at the University of California, Berkeley. She is also, nice transition, thank you, Mark. She is also the co-chair for that group you just heard of, the START, and it's thanks in part to her leadership with her co-chair that we've got 1,000 people signed up for that, and a huge responsibility to wrangle that. Flirkin hurting to the ninth degree. So Courtney, you're next, thank you.
Thank you, Sean, and thank you all for having me here today. It's been absolutely wonderful to work on this idea of the Habitable Worlds Observatory. In my presentation, I want to emphasize that the telescope has 3 words in its name. Habitable worlds is one of my favorite topics. As an exoplanet scientist, I think that is one of the most exciting things we could do, and I'm so excited to hear Dr. Grinspoon speak later today after our panel. But the O in Habitable Worlds Observatory is observatory, and as Dr. Clampin said, we will observe a wide variety of objects. On this slide, I'm going to show you a movie, but the movie is based on real data from JWST. These are observations of galaxies, allowing us to see very small galaxies that wouldn't have been able to be studied in this detail without JWST. And the galaxies have been placed in the movie at roughly the right distances, and then we fly through the galaxies. So let's take a look at that. As you watch, imagine that this is actually data from HWO. If it were, we would have ultraviolet, optical, and near infrared. That would allow us to do things like resolve star-forming regions in some of these galaxies. We can investigate the kinematics, the motions of the stars, and their compositions. That would help us figure out how those galaxies were built up over time. And as an exoplanet scientist, I would then wonder how many of those stars had planets. And we could consider doing more work on theoretical estimates of the frequency of life, not just in our galaxy, but in other galaxies. Focusing more on the cosmology side of things, the ability of HWO to detect very faint objects at high sensitivity and high resolution will also allow us to probe the nature of dark matter. So we'll understand the history of the universe much better. With HWO, we'll be able to study galaxies that are farther away at higher redshifts, so looking back in time effectively, the same way that we study the nearby galaxies today. JWST is still a relatively young mission, but it has already upended years of what we thought we knew about galaxies. So just imagine how much more we'll learn with a telescope the size of JWST and the wavelength coverage of Hubble. My extragalactic colleagues are very excited about the possibility of seeing these galaxies in the UV to then explore what they've learned already from JWST in the infrared at shorter wavelengths. Closer to home, the Habitable Worlds Observatory is also going to teach us more about the planets in our own solar system. So later today, there's a panel on interplanetary exploration. With HWO, we will be able to obtain high cadence, so frequent observations of places in our solar system. Out to the distance of Jupiter, which is the object shown here, we will be able to resolve things at near flyby resolution. So you could imagine if you had a mission that was on its way to Uranus, you could take observations of Uranus with HWO at a range of wavelengths and see exactly what was happening at the planet while your spacecraft was on the way. These observations, because they can be scheduled as needed, will allow you to track time-dependent phenomena, and they will then supplement the higher resolution data that you get from spacecraft as they fly by the planet. This image here is a real observation of Jupiter with JWST. We could do something similar with HWO, and we would get the UV. So we will learn more about the atmosphere and circulation patterns of our own planets. As an exoplanet scientist, I'm delighted by that because we have planets right here in our own solar system. If we learn more about them, we can learn more about planets around other stars. We can learn more about how our own solar system formed, and we can look for similarities and differences between our planetary system and other planetary systems. We will actually be able to address the question of why is it that our solar system has life? Is there something unique about our planet Earth or about the structure of the solar system? Is it that other planetary systems also have Jupiters at Jupiter-like separations and planets like Earth with life on them? Or might it be that with HWO, we find that most of the worlds that seem to have life on them have solar system structures that look totally different from our own solar system? We've started addressing the frequency of planetary systems like our own with current ground-based and space-based observations, but we aren't yet able to answer that question. Because today, if we had a solar system like our own orbiting another star that was actually pretty close by, we would detect one, maybe two of the planets in the solar system. We need HWO to allow us to detect Earth-like planets around sun-like stars. With HWO, though, when we use the coronagraph that Dr. Clampin described, we will also be sensitive to other planets in the system. So here you see a simulated image of what a nearby planetary system might appear to look like with HWO. We're blocking out the light from the central star with the coronagraph, and you can see the planets Earth and Venus and Jupiter come into view, and Saturn. In this image here, you're seeing them as pinpoints of light. We won't get an image like the one of Jupiter here. It's just too far away. But we could take these observations at multiple times and watch the planets move around the star, allowing us to figure out their orbits. We could also take observations at different wavelengths and take spectra, which will allow us to look at their atmospheres. For some of the planets that appear to be Earth-sized, Earth-distance, they might have atmospheres that look like our own. We could detect biosignatures, things like oxygen and methane in combination, and perhaps water, that show us that perhaps that planet has life on it that's looking for life like the life on our own planet. Or more likely, there's life on that planet and it's like little teeny microbes. But stay tuned to Dr. Grinspoon's talk to learn more about the diversity of possible life that could be out there. With HWO, we'll have a broad wavelength coverage, which is essential for allowing us to detect different types of life. If we go back in time in the Earth's evolution, the atmosphere changed over time. And Earth was inhabited for much longer than its atmosphere looked like this. And in order to see all of the stages of Earth's habitability, we need the UV to the near infrared. I'll close there, but I'd be happy to talk more about any of the wonderful science, and I really appreciate the thousands of people who are helping us flesh out these science cases.
Thank you, Courtney. Pass that one down, please. Our next speaker is Matthew East, who is a lead astrophysics mission architect at L3 Harris. And just as a note, we almost need a new word for the complexity of this, right? Everything Courtney just talked about was all about interdisciplinary science. We're going to hear about interdisciplinary systems engineering, and later on the interdisciplinary field of science policy. And it's almost like this is interdisciplinary science, and that's why I'm glad we have the diversity of voices we have here on stage today. So Matthew, take it away for the next part of this story.
Thank you very much, Sean. So this is one of several concepts we're developing for the Habitable Worlds Observatory. Right now, these concepts, we're developing them to learn about the trade space, learn about the mission architecture. What you see here is a large outer barrel assembly that surrounds the telescope and holds it thermally stable and protects from micrometeoroids. And in the aft here, you see the instrument modules. This is just one example of one of these concepts. There are a few elements that are likely to make up the Habitable Worlds Observatory. One of them is this roughly 6-meter segmented primary mirror. That will be building on the accomplishments of the James Webb Space Telescope. There's also this large secondary mirror structure that's off-axis, and that allows an unobstructed telescope with very high contrast. The stability of the telescope is exquisite. That is one of the two needs to see these Earth-like planets around sun-like stars. We need the stability, and we need to develop the coronagraph. Those are two technology areas that have been a focus, and industry and NASA have actually been doing development in the lab, test beds, and proving out these technologies already. There is a roadmap ahead of us that includes the Great Observatory Maturation Program to make these technologies and the architecture fully ready. And I believe that's a credible roadmap to see these smaller planets that are closer to their host stars. There's also these solar arrays. This is not cryogenic telescope like James Webb. It's actually warmer to enable some of the UV observations. The instruments include the coronagraph, a deep field imager, a UV instrument, and an extra instrument, which we're still defining what are the possibilities of what that instrument module could accomplish. This will be a serviceable mission. So it's not just a mission for our generation, it's a mission for future generations and future capabilities that may be compatible with it. So this mission does build on past accomplishments from flagships and other observatories of past. The segmented aperture, the coronagraph, the UV capabilities, all build on previous accomplishments. Right now, I believe the technologies are nearly ready to characterize habitable Earth-like planets. There's work to do, as outlined by the Astro 2020 Decadal Survey. That work, we have a plan to get there. It's the Great Observatory's Maturation Program. Right now, there's 3 rockets that may fit the Habitable Worlds Observatory, and we're developing these exploratory analytic cases like this design here in the middle of the bottom of the screen. In the future, we're building towards scalable modular technologies that exploit these new launch capabilities. and they're really creating a foundation for future of astrophysics. There's benefits from all of these new technologies, not just the large aperture, but the instruments and the sensors and all of these technologies that make up the observatory. And some of the benefits of those new instruments can work together and multiply together to really open up the discovery space. This will have more resolution. It will also have more sensitivity than Hubble. So it really opens up the opportunity for new discoveries, not just for exoplanets, but certainly orders of magnitude new capability for exoplanets and smaller, more Earth-like planets. Gene.
And our last speaker is Gene Tolleisen, who spent 27 years as the U.S. Senate staffer with time on the Committee on Commerce, Space, and Transportation and the Senate Appropriations Committee. And now she is the Vice President for Corporate Strategy at the Association of Universities for Research in Astronomy, or AURA. So, Gene.
Thanks. So, I'm holding it up. There we go. Oh, wrong way. All right. They don't, congressional staff are not good at PowerPoint. I'll just say that. So, how do we actually go from all of these great ideas, all of these great science cases, all of these trade spaces to actually getting the funding for this, not just going a little bit, but big? Of course, you know, we get the decadal survey and NASA says, great, let's do it. But there is a huge policy and budget framework around that. So you get the decadal surveys, it feeds into NASA, and it feeds into Congress, and it all just works, you know, lickety-splickety like that. But as we know, that's not really true. You know, Article 1, Section 9, which tells us that, you know, no dollar can be drawn from the Treasury except by law passed by Congress, means that, you know, unlike our colleagues in other countries, we can't just sort of executively, ministerially decide, hey, let's go for it, and it suddenly happens. Instead, Congress gets to play a role. The NASA itself plays a role, OMB, OSTP. So we've got the authorizers, we've got the appropriators, and everybody wants to have a say in this. And they all feed back on each other. But it's not just them. All of you out there have a way to feed into this, whether you're talking to Mark, whether you're talking to the authorizers, whether you're talking to the appropriators, whether you're talking amongst yourselves. And all of these inputs change what spits out at the end of this Rube Goldberg machine and translate into dollars. So it's not just enough to have a great science case, and it's not just enough to have a great technical case. You need the support of those thousands of scientists, and you need the support of industry, both to say that this is technically doable, but also to help with this whole Rube Goldberg machine to talk to the policymakers and both assure them that this is doable, but that it's not just the nerdy scientists who wrote this decadal survey, but that this is good for the nation. So we're going to keep turning these gears and see what happens. But the only reason these gears turn is because of the possibilities that Matthew talked about and the science cases that Courtney talked about.
Thank you, Gene. So I am struck by that last slide. This is working now, right? Yeah, okay, cool. I'm struck by that last slide, both in its complexity, and it reminds me of this like famous slide in the exoplanet arena. Courtney, you'll know what I'm talking about. It's called the planets are hard slide, where there's like all these lines intersecting and twirling around. And for me, I think the thing that I really appreciate is just the complexity in each of these arenas, and how important it is with people from different partners and types of partners here to help with that. Now is where we take questions from all of you on what you all just heard from these panelists. And so I'm looking around the room to see if we have any. I think we've got one in the back, and then I see one here. So let's start there and then here.
Maybe I'm geeking too much, but it would seem like a technical challenge would be the shorter wavelengths with the segmented mirror. And I'm just wondering, there's a fairly robust industry making large single segment mirrors for ground-based telescopes in the 6.5 to 8 meter range. And so I'm just wondering if you would, if that would be a consideration at some point from a technology selection perspective, as well as maybe multiple launches, given the decreasing price of launches?
Matthew.
A lot of those technologies that have been leveraged for segmented ground-based telescopes, they are in the trade space, and they are in consideration to support Habitable Worlds Observatory.
Thanks, Matt. I think there's a question in the middle, and then we'll come down here.
Hey, Sean, can I just...
Yeah, Mark, you want to add to that? Sorry, didn't mean to
Yeah,
preclude
I
other
also
answers.
just wanted to add, a lot of ground-based telescopes right now use materials for those mirrors that do not really fit with the level of stability that we're looking for from this telescope. And while we want to actively control it, we still want to minimize the control space that we need to control it over. So we're really looking at very stable materials like ULE, for instance, as the sort of baseline, optical content of the mirrors.
And we got a mic ready here. Questions on this side?
Am I up?
Go ahead.
I'm up? Oh, good morning. Thank you. In the trade space genre of questions, I'll be quick. Starshade, the chronograph is technically challenging, and I know it's the baseline for both Roman and HWO. Where are you guys thinking in terms of keeping a Starshade in the trade mix?
So Matthew mentioned that the telescope is serviceable. One of the ideas that we are considering as part of the trade space is having a Starshade that would fly later in the telescope's lifetime. In the HabEx report, they considered 3 different varieties and multiple sizes as well. One of those was just a coronagraph, one was just a Starshade, one had both. And in their analysis, they realized that it makes the most sense to search for the planets with the coronagraph because that's more nimble. And then if you want to do detailed characterization over a broad wavelength range, that's where the Starshade is powerful. So by having the Starshade as a 2nd generation instrument, it would time things appropriately. So we could find the planets first with a coronagraph. It also gives us more time to mature the technologies for everything, so that when we do fly the Starshade, it's an even better Starshade with more precise petals. And we will also, as we go through the design, we are keeping in mind the need of keeping the observatory both serviceable and ready for any types of future upgrades we might have. So for the Starshade, that would be Starshade compatibility. And then we're also just looking in general about what wavelength range is the most appropriate for biosignatures and what contrast range and how do those choices we make affect our science yield. So it's all connected, and we're doing a really thorough analysis now to figure out what the trade space so we head in the right direction as we start to narrow down.
Got a few hands up. Let's go to the front here.
I can shout.
If you shout, I'll have to repeat for online, so just pause 1 second. And then I think there were a couple, if you can keep your hands up in the middle section for the second mic, I think right there in the middle. Go ahead.
Thank you, and your enthusiasm for exoplanets is very exciting, Dr. Dressing. My question is, you talked about how there are 3 different launch vehicles that are capable of supporting the Habitable Worlds mission. I was hoping you could talk a little bit about how those launch vehicle capabilities are impacting the spacecraft design and the science, the ultimate science. Thank you.
One of the challenges at the time we were planning the Roman Space Telescope, there were 3 potential launch vehicles that were compatible, and at the point of selection, it was down to only 1 that was available for use. The same risk is recognized, and we're planning for that with the Habitable Worlds Observatory. We're looking for compatibility with these 3 launch vehicles, which means managing mass and volume of the package of the space unit. So the mass drives us to a lighter weight. It drives us to consider what's reasonable for aperture size, and it drives a number of other elements of the number of instruments we can carry, among other things.
Mark?
Let me also just add to that. So I said that we are following the recommendation of the Decadal Survey, and it's a very similar set of recommendations to what was in the NASA Large Mission Study as well. So we are not actually designing the telescope yet. We are focusing on maturing the technologies, and we expect to be doing that for a number of years. And then when we get to the appropriate point where we think our technologies are ready, we will conduct an independent review as the Decadal recommended, and then we will start doing what we call formulation, which is designing the telescope. And the basic philosophy there is you're better to design the telescope and the observatory once you know what technologies you're putting in there, so you can properly assess how they will work as a system as you put the design together. So we are thinking about large rocket fairings, and they will inevitably be a part of this program, but we are not designing to them anytime soon.
To address your point about the science, on the science side, what we're doing is almost technology agnostic at the moment. We're looking back at the Decadal Survey. We're identifying what are the science questions that they prioritized, and how does the science return depend on things like the ability to resolve a faint source at a certain separation. On the science side, we don't care how you resolve that faint source at a small separation, whether it's a trade for a larger mirror or maybe a better inner working angle or higher contrast. And we produce these charts that show us how many exo-Earths do we get for different capabilities. And then we pass those to the intermediate team that's looking at the intersection of science and engineering, and they pass it to the engineers who give them a chart that is how well can you resolve a small faint object close to a star as a function of something like mirror size.
Thank you all. Middle of the room.
So one of the questions that I had was, with the Artemis program, are you considering anything related to experimenting on how to build a telescope in space so you don't have to deal with future limitations on fairings?
So as I said, at the moment, we are not in the process of designing the telescope. With the current timelines and progress that's been made on assembly in space, and also, more importantly, the technical challenges we have with this observatory, which is making sure that we can actively control it at the level of tens of picometers over the control cycles. We're really looking at flying a telescope and not trying to assemble it in space and then figure out how to achieve the required stability and alignment.
Okay, thank you. One more quick question. Does anyone have a quick question? There, or in the very back of the room? Sorry, this is the last one. For anyone who's had hands up, please approach the panelists after or at the break.
Okay, I think this may have used to have been a silly question, but at this point, in the event that the HWO does find evidence of life, will there be a protocol for informing the general public?
Can I would like to, that's the perfect segue question for our next speaker. So the short answer is yes. The long answer is about an hour, and we're going to hear about it in about 2 minutes. Does that work? Okay, thank you. That's a great question. Let's thank all our speakers here today.